What's going on, everybody? This is Mr. Diamond. As you can see, I am missing my camera at school today, so you'll have to deal with this picture instead of my lovely face. So I apologize for that. We're getting into section 3, which is the conservation of energy. You've probably heard of a law related to that at some point, but we got a good quote from Full Metal Alchemist. I finally did find one about conservation of energy. Just had to think outside the box a little bit. Humankind cannot gain anything without first giving something in return. So we mentioned previously there were two broad categories of energy, kinetic and potential, but there's also two categories that we can use for forces as well. And those are conservative and non-conservative. And this also will apply to work. There'll be work that can be conservative or work that is non-conservative or come from those forces. Really, the forces is the important part. Conservative forces are forces where the work done does not depend on the path taken, only on the start and end point of the system. And non-conservative forces are the ones where the work done does depend on the path that is taken. It matters how you got to the end position. So I want to give you a moment to see if you can think of any examples of these. Then we'll get to that next slide. But take a moment and actually think about it. Try to think up, is there anything you can think of where a force would care only about where you started and where you ended, or a force that would care about how you actually got to those positions? So let's assume you're moving up a hill. As you move up the hill, you're going to have more gravitational potential energy, and then as you go down the hill again, you're going to lose that potential energy. It really doesn't matter to the force of gravity, to your gravitational potential energy and the work done by gravity, how you got up or down the hill. If you're just looking at the start and the end position, you will know your change in gravity. If you spiraled down the hill, if you did backflips, if you did cartwheels, if you took a helicopter way up into the sky, landed on top of the hill, all of these things don't matter. For the sake of gravity, all that matters is where the object started and where the object ended. We looked at where was its initial position, where was its final position for all of our gravitational energies. However, you would definitely have experienced a different amount of energy loss for cartwheeling versus flying versus walking, all of those different examples. And that's because the other energies involved are non-conservative. They care about the path you take. You will feel more friction if you go a longer path or if you take a more different path. And if you go through the air, you may have more air resistance. More energy is going to be needed by your muscles and your heart to pump blood and propel you forward. So all of these things are non-conservative, because it matters what you do. It matters the exact process that you go through to get to that point. But conservative forces, mostly things like gravity, and usually it's potential energies, they only care about where you started and where you ended. So to make this very clear, conservative forces result in changes to potential energy. In fact, it's going to be the negative of that. We usually label it as negative just for convenience of calculations. That's going to show up in one of the later slides, but don't worry about it for now. Non-conservative forces, though, do not result in only changes to kinetic energy. Kinetic energy, remember, is based on total work in a system. If you skateboard down a hill, sure, your gravitational energy is being converted to motion, but friction and air resistance is also going to affect your kinetic energy. So it does not have to be one or the other. Your potential energy also will affect how much kinetic energy you can get, but your kinetic energy will be influenced by those non-conservative forces. So again, conservative forces, potential energy, those two are linked together, but kinetic energy is linked to both. It's linked to both conservative and non-conservative forces, which is why we can expand our equation earlier. The net work equals change in kinetic energy. Well, net work would be all the types of work, and work will either be non-conservative or conservative. So it'll either be these two added together. So we can expand our equation a little bit. Work non-conservative plus work conservative is equal to the change in kinetic energy. And then we just said that potential energy is equal to our conservative work, or our conservative forces. Again, the negatives is to make the problem mathematically work out cleaner. We do that because we want positive work to reduce the amount of potential energy you have. If you do positive work, it will reduce the amount of potential energy that something has. So then we can take this and we can rearrange it, and we can actually figure out our non-conservative work, so the work done by things like friction, like air drag, stuff like that, or air resistance, whatever. Well, either one of those work, drag or air resistance, will be equal to the change in potential energy plus the change in kinetic energy. And it would matter whether or not they're positive or negative in that case. And that also means that if we assume there's no friction, no air resistance, no heat change, meaning there's no non-conservative forces, we can just assume that the change in potential energy and the change in kinetic energy is equal, aka that energy is conserved. So the long equation section over, that means if you ignore non-conservative forces, potential energy and kinetic energy should be equal, aka energy cannot be created or destroyed. The total energy in a system will stay the same. So if we know how much potential it had to do energy, we can figure out how much kinetic energy can come from that. If we know how much kinetic energy something has, we can predict how much potential energy it will have. So while energy can't be created or destroyed, we do know that it can change forms. Electricity can turn into thermal energy from a heater. Gravity converts energy stored in a position to kinetic energy. Nuclear detonation will convert nuclear energy into kinetic energy. All of this energy being exchanged is the fundamental concept that makes science different than math. I went on a rant about this already once, so I'm not going to do it again, but this is the key thing that makes it different. And this setup and being able to use this equation is what's going to allow us to do some a little bit trickier problems. Definitely trickier than the first couple of worksheets we've done this chapter. So this is going to take us to the end of the notes. I believe the next one is an example, so I'm going to work out those examples on a separate video that'll be attached to this. And then that's it for this chapter. We're just going to be working some different difficulty level questions for each of these sections here. If you have any questions, though, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a great rest of your day, everybody.